Hello, everyone. Can you hear me?
Hello. Yes.
Very good. Okay, I think we can start. Uh, Good evening, good afternoon, and maybe good morning, everybody. My name is Ahmed Al-Shamri. I'm the PIPESIM project champion based in Oslo, Norway. Thank you for joining our webinar today. This webinar is being arranged and coordinated by OPA Energy, which is a training consultation company based in Egypt, and they have several offices in the Middle East. Thank you, everyone for joining this webinar today. So unlike probably other maybe I would say academic or scientific probably presentations or webinar. I'm not going to show you any slides. Instead, I will just go right away to the subjects and show you a demo, real demo on the software itself. So today, I hope that I will be able to cover five probably basic topics. First topic is the how we do the compositional fluid modeling in PipeSim. And then we'll talk about how we model gas wells, including the different IPR methods and how we can simulate, the production using the pressure temperature profile or nodal analysis, and at the same time, we'll have a look into liquid loading issue using a Turner methodology in PipeSim. And then after that, we are going to try to tackle one of the main problems in gas production wells, which is hydrate formation. And we'll see how we can avoid the formation of hydrate or the risk of hydrate formation. And then eventually, if we have time, I'm going to show you the network optimization, how we can optimize the field-wide choke settings with using certain constraints and objective functions. So without further ado, I'm going to share my screen. So this is the screen I'm going to show, and then I say share. I hope that you can see my screen right now. So what we're looking at here is basically a PIPESIM well model, okay? And in the beginning, just for the sake of general introduction, in case you're not very familiar with PIPESIM, I'll just give a few minutes to talk about the user interface, how PIPESIM looks like in general, without really much details. If you need to learn more about the software, actually, I have a lot of YouTube videos that are already, published on the internet. OPA actually has hosted, I think, a couple of meetings with me and where I presented PIPESIM in general. But as I said, I'm gonna just give you a quick overview about PIPESIM and what are the main components of the user interface. So what you're looking at here is a well perspective. We call it well perspective, in which we are modeling a single well, and we simply have tabs here, different tabs for the different data. Okay. We have also what we call the network perspective. So as you can see here, there's a button that has a symbol of W, which stands for well, and then this means that we are under the well perspective. We can easily switch to the network perspective by clicking on this drop down, and you see N and network. And then when I switch to that, you will see the network perspective of the same model. And if I have multiple wells in the same model, I will be able to see them all here. But in this case, we're having only a single well, and whether you run it in the network perspective or the well perspective, it will be exactly the same, right? So now I will start by talking about compositional fluid modeling in PIPESIM. So if you see here on the top menu under the home tab, so we have the home tab here, and then we have insert, we have format. Okay, so those are the three main tabs that you can navigate through when you are in the network perspective. And whether you are on the network perspective or the well perspective, there are sections that are really shared. Like, for example, if I switch to the well perspective, you will notice that this section is shared data, and we have simulation settings and fluid manager. So switch to network, you see the same, but now we have flow line manager and zone manager in addition to the simulation settings and the fluid manager. So how we can, what are the options for modeling fluids in PIPESIM? So under fluid manager, if I click on this drop down, you will see that I will be able to use black oil, compositional, PVT file, or MFL file. MFL stands for multi-flash file. So for the black oil, basically this is where you can use PVT correlations to predict the fluid properties under different pressures and temperatures. Almost all the standard and famous PVT correlations are available, but as I said, I'm not going to talk about black oil today. It's just for your information. And we have the compositional fluid option. So PIPESIM has the capability to model the compositional fluid natively in the PIPESIM user interface. And if you'd like to have more advanced options for modeling fluid and using also the compositional characterization, you can go, for example, you can generate a .pvt file using PVT-sim, for example, or .mfl file using multi-flash. Okay, so for example, if I say I would like to use MFL file, then simply you will need to click on the plus sign, and then when you click on new, there's a seamless integration with a software package called multi-flash, you need to have a license for that. So when you click on new, this will automatically launch multi-flash software for characterizing the fluid. And here, as you can see, and once the fluid is characterized, when you save, basically, you need to export the MFL file here. It will go back as an MFL file, and then the connection will be removed. Okay, but again, we are now today to model compositional fluid. So I'm going to again go to the fluid manager and change the fluid type or fluid option to be compositional. Okay. So when you go to compositional, you will see that you have 3 tabs under the fluid manager. The fluid itself, how many fluids are there in your project? The fluid mapping, which actually maps each of the, if you have even 10 fluids, 20 fluids, whatever, you can map each fluid with a source, with a well, right, using the fluid mapping. But since now we only have one well, okay, that means I have one source, then under the fluid mapping, we see that we have only one row, okay? So now well 1, which is this one here, is mapped through the source, which is completion, into a fluid called medium oil A. So where is medium oil A? It is here under the fluids tab. So this is medium oil A, right? Before I show you the composition of medium oil A, let me just show you the 3rd tab, which is the components or the component and model settings. So when I click on this, you will see all the PVT packages available for you to use inside PIPESIM. So for example, the PVT package can be either multi-flash. So this is the engine that is going to characterize the fluid, utilizing all the composition that you will enter in this interface for each fluid. Like for example, I can say that the PVT package is multi-flash or symmetry. So symmetry is an SLB product. We have a process simulator called symmetry, and part of that process simulator, we have a fluid package called symmetry. So if you want, you can select symmetry and then use symmetry as the main fluid characterization package. We have also E300, another package, which is coming from the reservoir simulator Eclipse. And you can use GURC if you want, okay? So this model, I'm using multi-flash, but at the same time, I can click simply into symmetry. And when I click on symmetry, basically, the options for the equation of state will be slightly different. And then you will see that if I select symmetry, then the equation of states available for me is advanced Ping-Robinson and advanced Ping-Robinson for natural gas, 2 Ping-Robinson and SRK, right? So these are the equation of state that I can use to characterize the fluid using the PVT package symmetry. So if I select the second option here, okay, now you see that I have, for the viscosity, I have a list of viscosity options. So these viscosity options are used by the flow model to calculate the pressure drop, the frictional pressure drop, and also to calculate the different other PVT properties. So as you can see here, there is a list of viscosity models, and all these viscosity models are actually, again, used by symmetry. All right. If you select multi-flash, then you will see different viscosity options. Okay. Now, these are the default methods for the volume shift correlations, critical property correlations, thermal coefficients, and so on. Okay. Now, each of these components now, as you can see here, we have all this list is coming from symmetry. All right. So now I can identify only the ones that I have selected for my fluid. Like for example, if I highlight only the selected, then it will give me the list of the components. So now these are the components that I'm going to that are available in my fluid. We have methane, we have ethane, propane. So now this is just the list of the component. I'm not talking yet about the composition itself. Okay. You will notice that we have standard components in black, and then we have green components in which are user-defined components. So if I double-click on any of these, I can see that these are editable fluid properties. So in case you do not have you have a component which is, or you have a lump component, for example, or you have a component or a fluid a fluid component that is not available in the list, which is a big list actually. As you can see here, there's a big list here of standard components. Then you can create your own by simply clicking on new. As you can see here, those are previously created. So if you click on new, you can add a new user-defined component. You can name it yourself, and you can define the properties, and it will be used in your fluid. So again, what have we done so far? I will just repeat. So what we have done so far is that we clicked on the fluid manager. This model already has a fluid with a previously created composition. So now I click on composition fluid. I have 3 tabs. One tab for the fluid. This is already created fluid before. There is a fluid mapping between the fluid name itself and the source. And we have the components that are available in, or that are used in my fluid. Now I need to know what is the composition. Then you can simply go back to the fluids tab and double click on this fluid. And of course, as I mentioned before, if you want to add a new fluid, you can simply press on this plus sign, and now double click. You can start define. These are the components that I have selected before, and then you can define your composition. Okay, so now suppose that you have 2 or 3 fluids. Then you have to, in your list, in your component list, you have to put all the components for all the fluids. And if there is one component not available in another fluid, you can simply put the composition to be 0. Like, for example, I can put, let's say, maybe let's say 60 moles methane, then 15 ethane, 6 propane, 4. And as you can see here, the mole fraction is being calculated automatically. As I add, you will see that the phase diagram is automatically created. Okay. Now, butane, for example, 3, I'll put 3, 3, 3, 3. And then I can put, for example, 1 or 0.1 nitrogen, 0.01 CO2. Okay. And now, as you can see here, now it's becoming more phase diagram. As you can see, this is really quick. And then we have also the heavy components or user-defined components. I can say, for example, that I have, let's say, 10 moles and 25 moles of these 2 components. And now you will see that the phase diagram has changed. Now, this is a powerful interactive fluid modeling interface that I haven't even started my case or my simulation. This is an interactive fluid characterization interface. Like, for example, suppose that you would like to see what are the fluid conditions. If you define your composition like this, what are the fluids? What is the phase status under different pressure and temperature? Like, for example, what if the pressure was 3000 psia and the temperature was, let's say, for example, 230? Okay, then we are here. We are inside the phase diagram. Okay, this is the liquid and gas, percentage, mass fraction. Okay, for the methane. And then you see that the GOR is 215. This is definitely an oil, well with certain, GOR. Okay. Now, as you can see here, this is using 3,000 and 2,230. You can now go to the full mole fraction for your fluid. So this is the gas mass. This is the mole fraction for liquid and gas for the overall fluid. Okay, this is the mass fraction. This is the volume fraction. So this is liquid and gas. Okay, and then you see all the fluid temperatures, fluid properties. Okay, all that is instantaneously calculated. Okay, now you go and tell them, no, my probably I don't have, let's say I don't have this component. So I say, for example, this is 0, and now this is 0 also. Then you have a completely different fluid. And as you can see here, based on this pressure and temperature, we are liquid, okay? Because we are here. And now you can start, yeah, let's say, reducing the pressure, and you say 2000, for example, 300 or 2000. Then we are here, okay? And now as the pressure goes down also, then we'll start entering, like for example, if the pressure becomes 1500, then we are almost there. We are still, so now we are gas, because we are on the right hand side. And then once we enter, because this is our critical point, then once we enter, so for example, if the temperature was let's say 200, then this is our gas fraction, this is our oil fraction. As I said, all of this is interactive. This is a very useful tool for you to evaluate your fluid under different pressure and temperatures without actually running the simulation. Okay. Now, depending on, as you can see here, since we have a little bit of CO2, we can see the solid CO2 line. This is using symmetry fluid engine, okay? And what we can also see, suppose that if I go and increase the water moles, let's say if I have 5 moles of water, then I will start seeing the hydrate line, okay? And the water line. So all of that is interactive. All of that is, using the compositional fluid engine, which is symmetry in this case, and I can simply do all my calculations to know my phases without actually running the simulation. Okay. Now let's say that I'm done. I'm happy with my fluid. Everything is fine. So now I can go and as you can see here, under this pressure and temperature, this is gas, right? So so now I have created, as you can see, I have created 2 fluids, right? So my initial fluid, which was, medium oil A, is connected to the completion. So right now, let's in order, because this model was has, I think, an ESP, so it should be an oil well. So that's why I'm not going to change the mapping. So I'm not going to change this completion to be connected with the other fluid. Okay, I'm going to still use the same fluid, right? So now, even I have 2 fluids in the system, not only one will be used, because right now, using the fluid mapping, I have only connected this fluid to my completion, which is my source. Great. So now what do we do? We're done with the fluid composition, okay? And now let's have a look into our well, okay? And run it. But since this presentation is only about gas, so I'm not going to spend anything on ESP. So let's have another well, another case with gas. So I just wanted to use this project to describe the composition fluid option in PIPESIM, and how we build fluid, and how we do the mapping of the fluid. Okay. Perfect. So I'm going to close this project and then open another one, which is basically a gas well. So this is a gas well that I took from the case studies that are installed with PIPESIM. It's called fractured gas well. And if you have a look into the fluid itself, so if I click on the fluid manager, we're still using the composition fluid option. Here we're using multi-flash. We're using the SRK equation of state, Peterson, as our viscosity. If I highlight only the selected, then I see these are the components that are used. So I'll just expand this to have a look. Okay, so these are the components, right? And now let's have a look into our fluid. So when I double click on this fluid here, then the fluid will appear in this screen. And as you can see here, I have the water line and I have the hydrate line. Okay. Now, as I said, I can also change the conditions to have a look and evaluate different pressure and temperature. So for example, at 2000 pressure and at 200 temperature, 200 Fahrenheit temperature, we are here, okay? And this is basically the, so the mixture here is mainly gas and little water, okay? Good. So now this is our well. Let's have a look into the well description, okay? So this is a well, right? What you're looking at here is the well cross section. So obviously it's a deviated well. So the well type is production. The deviation survey is like this, okay? And then we have the heat transfer. So now at measured depth of 160, we have a ambient temperature of 45. So apparently this is a well that is probably subsea, okay? So we have this is the manifold. And then we can also look into the tubular. So have a casing, just one casing up to 12,500. And then we have a tubing up to 11,000. Okay. And then we don't have any downhole equipment except the nodal analysis. And we have a packer here. This packer is used to block the flow in the annulus. We do not have any artificial lift. The completion now is described using a single point geometry or single point fluid entry. And we have Darcy IPR. Okay. Now, when you use Darcy IPR, you can either define the IPR basis to be liquid phase, or the basis is liquid or gas. So in this case, it's a gas based. And as you can see here, this is the IPR. We do have other IPR methods for gas, such as Fitkovich back pressure equation for Scheimer or hydraulic fracture. But for the time being now, we're using gas. We're using Darcy. And for Darcy, we have certain parameters and different options. One of the options is called use transient model, and transient model is basically when the completion or when the well has not reached its pseudo steady state conditions. Okay, so that you can have the time element. So for the time being, this IPR is for 6 hours. This is the porosity and this is the compressibility. If you think that your completion has reached its pseudo steady state, then you basically don't use this transient model, and then this is the IPR. We have the reservoir thickness, the borehole diameter, and the permeability, and of course these are just different input for Darcy. Now, when I click on the fluid model, I see that this is the fluid that we have already defined here. Just as a reminder, when I click on the fluid manager, I have a fluid called gas water. This is gas water. And then the fluid mapping is actually combining the completion, which is this one here, with the gas water, right? And now if I click on edit, this will actually open the fluid manager again. So, but it will go directly to the fluid composition. So when I click on edit, you will see that it will all the way again to my fluid description, correct? Now, what if you have defined your fluid composition, but then you have measured GOR or CGR during the well test, and then you don't want really to go and update the composition itself to match this new condensate or new phase ratio, new GOR or new CGR? Well, then that's simple. You can simply go to the fluid model under this tab here, under the completion tab, and then you can select an override method. Like, for example, you can say override method, you can go to phase ratio. And now, as you can see here, this will, under standard conditions, the GOR is infinity, meaning it's all gas, right? And I would like to make it a little bit, I'd like to have a certain of condensate. So I can change the override method and I call it OGR, which is condensate gas ratio. And now I can put, for example, 10. stock tank barrel per million. So this is the condensate ratio, okay? And as you can see here, we have 100% water cut, meaning that if I do this, then that means the water cut. So the fluid that the liquid that will be part of the gas will be completely water, right? So I can also change that by playing with the gas water ratio, for example, or WGR. So for example, if I say I want to play with the WGR, and then the WGR is, for example, 2. So now what have I done? I have actually created a new phase ratio. And when I'm going to run my simulation, there is an algorithm that will utilize this phase ratio to adjust the composition so that it will match your, OGR and WGR. To see how that works, you can simply, if you go to the fluid composition, then you can specify the phase ratio like we're doing here. So if you specify the phase ratio, okay, and you tell him, I know my OGR to become 10, if I remember, and my WGR to become 2. Now it's going to do the calculation. Let's hope that this is something that it can find. Apparently, it's not possible under this. Let me see if I have, let's say, 2,000 and 200. So probably this is just maybe it's just a stupid number. So I'm going just to calculate. Let me just not mess with it, okay? Because probably the components are not enough to to find the new composition. So anyways, let's not mess with it, okay? Let's just use the but this is just the idea. If you want to override any composition, you can simply go here and define your phase ratio. However, you have to be careful because it depends really on the components that you have specified. So it could be a way that it's almost impossible with this composition, okay, with these components to define a composition, a new percentage that will honor your defined condensate. And apparently it's because we don't have heavy components. That's why it cannot find really good CGR or condensate gas ratio. Okay, so this is purely gas. Okay, perfect. So now we have, what did we do? So we said that, okay, this is the generator production, this is the deviation survey, we defined the composition, the tubular is casing and tubing, and then we have the completion defined as Darcy. So when I go to the reservoir, this is the reservoir pressure, this is the temperature, and now we have also what we call the skin calculation. So this particular case here, we're modeling, has a frac and pack, okay? So now it's a fracked and then packed. So we have the half length of the fracture, the fracture width, the propant permeability, and then is it choked or not, and then and the rest of the components. And as you can see, based on this input, it will immediately put the frac pack skin. Okay. Now, of course, if I don't want that, I can simply uncheck this value and then uncheck the choke, and then basically just define the if I don't have any frac pack, then so these options are interactive in this screen. So you don't need to, you can simply depending on your options, you can go and select whatever you'd like to do. So right now, let me just uncheck these options. So now we have I can even delete the gravel pack. It will not complain, because right now we don't have frac and pack. So now this is the calculated now skin. As you can see here, we have the mechanical skin is 2.88. This is basically based on the perforation, the diameter, the perforation interval, and so on and so forth. Okay. So now what is next? I would like to run this model and see if I will be suffering from any liquid loading. Okay, so click on the PT profile, or let's run a nodal analysis. Okay, and you'll see that we have a surface equipment. So we have this line, which is 12 feet, and then there is another line which is 6,000 feet, and then we have a choke. Okay, so now we are going to run this using PT. Let's run using nodal analysis first. So when I run nodal analysis, it's going to have so this is my nodal point. So we have the inflow and the outflow. And as you can see here, this is our operating condition. So now this will, under these conditions, is producing 33 or almost 34 million standard cubic gas at the nodal point. Okay. Now I would like to learn more. So if I click on view operating envelope, okay, and let's analyze this. So I'd like to have probably, let me put a limit. So for example, we can stop at the, let's say, the wellhead, okay, and then we can say that the wellhead is maybe, I don't know, probably 1,000. And then when we run, so we have this scenario here, and we can look into the profile results. So the profile results is showing us the elevation versus the pressure as a first point. And now, as you can see here, this is the pressure drop across the completion. This is until it reaches the tubing. So this is at the tubing, and this is basically at the wellhead. Now, what else I would like to see? So now I would like to see, for example, much more data. So I can click on show grid. And now this will bring me all the results. Okay. Now, as I said, we need to look if we are going to suffer from liquid loading. So when does the liquid loading happen? So liquid loading happens in basically two phases: annular mist and annular. Okay, because this is where the liquid is on the inner surface of the tubing, and then it will start falling down. So the droplet will start happening. So that's why when I run this, I can define certain parameters. So I can click on select columns, and then if you type loading, I can see the liquid loading gas rate. I can see the liquid loading velocity and the liquid loading velocity ratio. And you will notice that the liquid loading, now this is LLV, this is liquid loading velocity, LLVR, this is the liquid loading velocity ratio, and liquid loading gas rate. So why we don't see these calculations at the different rows? Because basically when you have a segregated phase regime or distributed, you don't have the ability, based on Turner criteria, you don't have the ability to have liquid loading possibility. So right now, when under this depth here, okay, we might start having liquid loading. All right. And now let's analyze this data. So number one, the liquid loading gas rate, okay, this is flowing, huh? This is what? This is the minimum gas flow rate, below which you will not have enough energy to carry on the liquid, the condensates with you. Okay? And that's why you have to always produce higher than this rate. This will be translated into what is called the liquid loading velocity and the liquid loading velocity ratio. So how much are we producing right now? So the gas rate, how much is the gas rate? The gas rate right now, if I go to the select columns and then gas rate. So this is the stock tank gas rate, all right? or let's go to the flowing gas rate. Okay. So the flowing gas rate is this one. So we are way higher than the liquid loading gas rate, which means that we're okay. We do not have the risk of having liquid loading. And this is indicated by this ratio. As this ratio increases, that means the liquid loading velocity is becoming closer to the minimum. If we have one or more, that means you have a risk of liquid loading. Okay? So in this case, then, we do not have any liquid loading. Now, let us try to play with the conditions and see if we can reach this liquid loading. How can we do that? Well, we can look into the completion pressure, and let's start by reducing the reservoir pressure and see, as the reservoir pressure depletes, okay, then are we going to be closer to a liquid loading issue. So I'm going to the inflow sensitivity completion. The variable is going to be the reservoir pressure. And now I'm going to start with maybe 2,000 up to 4,000. And then the step will be 250 psi. Let's start with probably 2,000, too small, 2,500. And then when I click on OK, so I have created these steps. So now I'm going to run inflow sensitivity. I'm going to run sensitivity analysis by simulating the reservoir drainage. The reservoir pressure is being reduced over time. So now let us see if at certain pressure, we probably are going to maybe going to have liquid loading issue. So now I click on run. So apparently no, because here we're having I would say very still very high rate. So what I'm going to do right now is that I'm going to make the outlet pressure go all the way to the manifold. I'm going to define the choke. So I'm going to put a choke here. So I'm going to reduce the choke size. So the choke size is 1.5 now. So if I'm going to make it, let's say 1 inch, and see how are we going to operate now. So what did I do? So I have changed my boundary condition. So the branch will end at the manifold, which means that the pressure that I'm specifying here is far away from the wellhead. We have a flow line of 6,000 feet, and we have a choke. So now, first of all, let's see if this well will operate at 4,000 even. So now click on run. So we are operating, and this is still good. Now let's go and run the sensitivity again. Reservoir pressure again, 2,500 to 4,000, and step 250 psi. Run. So we are on at 2,500. We are around 15. So let me also make it a bit more difficult. So I'm going to start by 2,000 up to, let's say, 3,000. Step 250. Let us see if this is going to reduce the rate more. So now let's evaluate. So now we're producing at 2,000, producing 9 million. So what I'm going to do right now is that I'm going to click on profile results. And then let's select only the first one and then go to show grid. And now let us see. So now, so we are still in good shape. So probably because I think we don't have, maybe because we don't have a lot of condensate. So let me just, so this is just gas and water. So what I'm going to do right now is that I'm going to increase the condensate, the heavy component. So I'm going to make 20% of heavy component. Let us see how much is the GOR. I'll make it even more, so 30. Okay, so now I think this will become much more difficult now. So let us see if I run the PT, if I run the nodal again. So now, as you can see, I have changed now the fluid itself. I have added more heavy components, and now we're seeing now the well actually start to become, dead at this pressure. Okay, so, and as you can see here, so now it's actually looking into the liquid. It thinks now that the well is liquid, but this is now good. So now if I go to the profile results, okay, and I say show grid. So right now, let us see. So it became now even oil. So we're not seeing the you know the required phase behavior in order to, guys, I mean, you got the idea, right? It's just I'm just trying to find a difficult way to find a condition where we can have liquid loading, but this is the idea. So basically, you will need to look into the liquid loading ratio, liquid loading velocity, ratio, and if your liquid loading velocity ratio more than 1, then you will have a risk of having liquid loading. Okay, good. So let's move on to another example. Okay. So what I'm going to do right now is that I'm going to have an example where we have a subsea oil well. I'd like to describe hydrate formation. The same concept, of course, applies to gas. So let's have a look into this case. So again, this is compositional. So when I click on this, we have actually two fluids. So we have oil and we have methanol. So if I click on oil, we can actually we know that there is actually a component of methanol that is 0 right now, because I'd like to see the impact on the methanol when I inject. Okay, but if you would like to see the impact on methanol on the hydrate line, you can of course add it here. Okay, add the composition of methanol into the fluid itself. So what is this well? So now this is the well. So we have an ESP. It's an oil well. Okay, we have an ESP. Sorry, we have an ESP, and then we also have a completion. This completion is using now relative permeability data. This is just for demonstration purposes. Okay, we have also Darcy IPR, and then we have, this is the skin data. All right. So now this is the fluid. So under standard conditions, so this is the GOR and the water cut, but I'm not going to change that. So what do we have? Let's have a look into, if I run this well and I see if I'm going to suffer from any hydrate. Okay, so I click on the well. I'm in the network perspective, and I can click on the PT profile. The default is temperature versus total distance. Okay, so now when I run this scenario, this is the fluid temperature. So this is on the y-axis is the temperature, on the x-axis is the total distance. So this is obviously the completion, and as we go up, right, we're reaching probably the wellhead somewhere here, and this is the flow line. So as you can see here, we have a choke at the wellhead. Then we have an injection point called methanol. We're injecting 0 methanol right now. We have the downhole multi-phase booster. Okay, we have a tieback. This tieback right now has no insulation, so it's using the heat transfer calculation, using the basically the you know the heat, the temperature of the surrounding. So this is the heat transfer. So this is the pipe conductivity, and it is basically a subsea line. Then we have the riser. This riser is here. So this is the riser profile. This is the depth, this is horizontal distance, this is the ambient temperature. And as again, also we're not adding any coating. The surface temperature is 80, and this is when it reaches the air section. Okay, so now, and then we have the piping at the surface. We have a choke, and then we have another pipe. Okay. Now, when we run, you will see that all this profile is for all the pipes here. We have the tieback, we have the riser, the piping, and so on. And now I'd like to see if I will be suffering from any hydrate. Okay. All I need to do is that I would like to add on the right side, on the right y-axis, I would like to add the hydrate formation temperature. So this is the hydrate formation temperature. I need to use the same scale. So right now, this is the same scale. What do we have here? So this is the hydrate formation temperature, and this is the fluid temperature. So obviously, the fluid temperature is falling below the hydrate formation temperature, which means that we have a risk of hydrate formation at this depth onward. Okay. Now, what do we do? So we can have two things. We can do two things. Either we start injecting methanol and see the impact, or we can see if adding insulation to the riser and to the tieback will be even a better, a better solution. So for the time being, I'm going to, this is the PT profile. So I'm going to go to the PT profile. And now let's put sensitivity, okay, on the methanol injection. Okay, so as you can see here, we have this methanol object. So now I'm going to sensitize injecting the methanol liquid flow rate. So 0 represents no injection. 100 barrels represents 100 barrel of methanol per day injection, and then maybe 300. Of course, this is becoming more expensive, but let's have a look what will happen. So I click on run, and now we will have the 3 cases. So this is the fluid temperature. Obviously, the methanol is not changing the fluid temperature much, but now I'm going to add also the hydrate formation temperature. And as you can see here, we have, this is the hydrate formation temperature. We are still, I need to use the same scale, sorry. So as you can see, it's obviously the hydrate injection didn't help much, okay? So now I'd like to evaluate if adding coating will be much more efficient, okay? So right now I'm going to stop the methanol injection. And now let's go to my tieback, okay? And let's add, let me check here. I do have actually a previous example where I have added, yeah, so we're going to add, on the heat transfer, we're going to add coating here. So I'm going to put 2 layers. One layer with a thermal conductivity of 0.15 BTU per enthalpy degree Fahrenheit per foot, with a thickness of 0.1 inches. And then another layer of 0.2 thermal conductivity with a thickness of 0.15. So now I have added 2 coating layers on the tieback, and then I'm going to also take the same, and then I will add it to the riser. Okay. So now what did I do? I have added coating now. This will help us now maintain the fluid temperature. Okay, and hopefully this will help us not reach the hydrate temperature. So now when I go to run the PTA profile again, now I'm going to add the hydrate formation temperature. And as you can see here, we are now, so this is the hydrate formation temperature. We are still, you know, below. Okay, no, I need to use the same scale. Oh, only here. Okay. Now, in this, of course, it's much better, but now we can investigate the methanol injection. However, let us have a look into a better, probably, visualization of the result. So now, how do I see this on the phase diagram? So what I can do is that I can simply go to the phase envelope here, and then you will see that when I run this again, so this is our PT profile. So this is starting at 7,000. And now this is entering this of course, liquid. We're entering the bubble point. And now this is where we are actually passing the hydrate line. And that's why when I put the hydrate formation temperature, it's basically this region here. Okay. So again, this is an excellent way of knowing where is the risk of hydrate formation going to happen, and maybe I can add additional probably insulation to the pipe. So here I think this is how much is this. So no, this is really not much. Probably I can even add another layer, or add, start having injection methanol to also evaluate if we can avoid further the hydrate formation. Okay. I think we covered the main topics. The last topic is the network optimization. Okay, so let me open this case here for you. So now this is a network. Okay. And the wells are, so this is black oil system. The fluid is actually gas, but if I'd like to have a look into how much is the the GOR. So basically if I click on the fluid manager, so now this is the GOR of the different fluids. Okay. So obviously we have high GOR, which means that we are either gas or gas condensate. Okay. Now, if I'm going to run this network simulation, all right, I'm going to see how much GOR are we having at the sink, which is, in this case, I can filter into the sink. So now we're having 174,000 barrels of liquid. Out of that is 147 almost oil. And then we have 628 million of gas. So, and this is the stock tank GOR, 4,200. Suppose that I would like to reduce the gas rate, right? And how do I do that? So because now I know that I don't want to jeopardize the oil production. I would like to limit the gas production, but at the same time, I would like the optimizer to tell me how do I distribute the chokes. Because right now, each of these wells is connected to a choke, and the choke diameter is different. So most of these wells are fully open, okay, in terms of the choke. So now, since now I know that the GOR of the wells are different, I would like to reduce the GOR. Let's say, for example, I would like the stock tank gas rate not to be more than maybe 580, for example. but at the same time, I'd like this less contribution of gas to come from the wells with high GOR. Okay, so I'd like to have more oil to come. All right. So how do I do that? Basically, you can go do that using the network optimizer, because right now I have done the calculation using the network simulation. And now you can go to the network optimizer. So I click on the network optimizer. And now under the network optimizer, you see the boundary conditions. And then you see the initial conditions. So the initial conditions are actually the ones that are currently on the wells. Okay. So now I would like to go to the sink, and then let me put a maximum GOR if I want. So for example, how much is the GOR here? The GOR is 4,250. I'd like the GOR not to exceed 4,000, for example. Okay. So I put 4,000. And this is, remember, on the sink level. This is on the gathering point. So I don't know how to change the choke settings so that I put this maximum GOR limit, but the optimization control is maximize oil production. So you see, this is a mathematical problem, because from one hand, I'd like the GOR not to exceed 4,000, but at the same time, I would like to keep the oil production maximized. Okay. So now I will run. So this is the previous run. So let me just now go and make the calculation of the optimization. So I have a previous run, so the wheel curves are already generated. That's why you see it a bit faster. But normally, if you're running the first time, I mean, you'll need probably 20 minutes maybe to generate these wheel curves. So the optimizer is trying to find the choke settings so that it will honor my total GOR, but at the same time, trying to, shut down wells, not shut down, but choke back wells with higher GOR. So let us see if this will be successful. Again, this is an automatic mathematical optimizer in which it will try to change the choke settings simultaneously on all the wells so that it will honor my constraint, and at the same time it tries to maximize oil production. So obviously I think the oil production can be affected, but because maybe there is I have to sacrifice oil production in order for me to constrain the maximum GOR. Okay. So while this is running, let us see if we have any questions. Do we have any questions? Let's see. We can open the floor for questions, guys, while this is solving. If any question, please type them in the message. Type them in the chat. Can ask any question even from the previous topics. When there are different hydrate curves for different chemical rates, how you implement all of them in the simulation. So basically, at each node, when you inject a different hydrate inhibitor, at this particular node, the composition will be mixed. And then it will come up with a new hydrate line with a new hydrate temperature, and then it will perform the calculation. So all that is done at every node if you have an additional hydrate, let's say, injection. Okay, and you can also look into that also when you do the interactive compositional modeling. You can have different composition, different mole percentage of the different hydrate, and see how the hydrate line is changing. Okay, so it did not converge, so probably that was a difficult GOR constraint. Okay, let's put a different maximum gas rate if it's possible. So now the gas rate is 628. So if I put maximum gas rate of 600, let's see if this can be an easier problem to solve. Okay, so did I answer your question, Amir? Thank you. Yes, so again, let me just have a quick recap on what we have done. So we described how we perform compositional modeling. We say that you can add a fluid here, and then you define the composition. These are the components that you can select for describing your composition, and this is the interactive phase diagram that can be used in PIPESIM, and you can define specific pressure and temperature condition at which the fluid will be flashed. The flash will be calculated. One thing that I didn't probably explain is the different IPR methods that we have for gas. Like for example, we have trilinear IPR for unconventional completions, unconventional reservoirs, in which you can define the number of fractures, the fracture halving. So this is the unconventional reservoir. We have also, if you have, for example, if you go to the single point and vertical, you can also have, let's say, the back pressure equation, where you specify the CNN value. Let's say, like for example, C is 0.001, for example, and N is 0.98. So this is our IPR. Or you can have your test data, okay, where you specify, tell them, okay, at the production of 1 million, then the PWH was 250, and then at 5 million it was 1980, and then at, let's say, 10 million it was or 15 million, for example, it was, let's say, around 1500. So this is now I have constructed my IPR using test data. So this is another way of representing your IPR. So yes, so now we have converged. So as you can see here, we have the total gas rate is 600 million, and now I can go to the chokes, and then I can find the new choke sizes. So as you can see here, it had sometimes to actually shut down wells completely. Okay, and if I'm happy with this, with these wells being shut, I can simply publish the optimization results, and then this will be sent back to my network. As you can see here, this is my network now, and I have new wells that are shut, okay, because they have high GOR content, and this is the only way that the optimizer was able to honor my constraint or limit. Okay. Okay, when there is a possibility of wax and asphaltene in a field, the remedial methods for or mitigations does not have negative effect on each other. If yes, what is the best method to avoid both flow assurance issues in the field? So wax and asphaltenes, although they are in the same, let's say, family of of hydrocarbon solids, but they are pretty much different when it comes to the inhibition, inhibition, because there are different inhibitors for asphaltenes, different inhibitors for wax. Okay, usually wax is better avoided by trying not to reach the wax appearance temperature. Asphaltene is pretty much different. Asphaltene is an envelope, wax is a line. So when it comes to trying to avoid both of them, you will need to inject two different fluids that will over time going to start to melt or try to dissolve your solids. Sometimes it's impossible because it becomes thick, so thick and so hard, so that the chemical injection won't be able to treat them. And that's why it's very important that you start discovering and exploring these solids early enough and try to treat them by scraping, by injecting special inhibitors early enough, so that the problem doesn't appear more. Okay. So, any more questions? I think we have passed the hour. So, guys, let's connect on LinkedIn. So, if you have any specific question, and you're a PIPESIM user, of course, please don't hesitate to contact me. And I'd like to thank OPA for arranging this webinar. I believe this webinar is being broadcasted on YouTube. It's going to be recorded and available for future, in case you'd like to learn more and review some of these techniques. I hope I didn't inject a lot of information in a short period of time, but that's the nature of webinars. We have a short period of time, and then the only way to learn is actually to start to listen again and try to repeat these steps yourself, so that you can learn and it becomes useful for you. So with that, I think we have reached the end of this webinar. I'd like to thank you all again, and thank you. That's all. Have a good day, good evening, everyone. Bye.
Thank you.